it doesn't make any reference to whether A and B are finite or not. So this principle that two sets of the same number of elements, if there's a bijection between them, it can apply equally well to finite sets and infinite sets. The definition doesn't really care whether the sets are finite or infinite. So let's start to look at some examples. These are some very familiar infinite sets to us. The natural numbers, basic counting numbers, 1, 2, 3, 4, etc. The integers, which are the positive counting numbers plus a load extra, plus 0, and all the negative versions of the natural numbers. And then you've got the rational numbers, which is, you can think of in one way as all possible fractions that you can form, all possible p over q. P and q are integers, but the q must be non-zero. And then you've got this, in some senses, bigger set, infinite set, the set of real numbers. It's the set of all possible positions on the number line, on the continuum. These are all infinite sets. I think we can agree on that. Okay? But what sizes do they have? Okay? So that's what we'd like to explore now. So, is Z bigger than N? N, the natural numbers, is 1, 2, 3, etc. Z, the integers, well, it has 1, 2, 3, etc. in it. It also has 0, and it has -1, -2, and so on. They're both infinite. But it kind of, when you look at it in some ways, it kind of seems like the integers are twice as big. Surely the integers are twice as big. Because they have all the natural numbers in them, and then kind of another whole copy of the natural numbers with negative signs attached. And that's the kind of initial naive view that we might have had. That would be the kind of pre-Cantor view, is that, well, yeah, they're both infinite sets, but the integers, yeah, there's even more of them. Okay. But by Cantor's definition, they should be regarded as the same size. We can certainly say that the natural numbers, it's natural. It makes sense to think of the natural numbers as a subset of integers, and it's certainly a proper subset, because the integers contain lots of other numbers that aren't in the natural numbers. But under Cantor's definition, they should be regarded as the same size. Because we can construct a bijection between them. Bijection by the natural numbers Z. Okay, so here are the natural numbers 1, 2, 3, 4, 5, 6, so on. Here are the integers 0, 1, 2, 3, -1, -2, -3, -4, 4. But you have to construct it carefully. I mean, one way of trying to define a mapping between them is to send 1 to 1, 2 to 2, 3 to 3, 4 to 4, 5 to 5. Okay, that looks like a sensible mapping. Map each natural number to its version of it in the integers, but then you're going to exhaust all the natural numbers, mapping them up to all the positive integers, and you won't have mapped anything to the negative integers. So that won't be a surjective map. But when you think about it, you can easily do this. So what we're going to do is we're going to map. Brain. Yeah, you just map all the odd integers to the positive integers. So 7 here. 7 here, we map to 4. Okay, we continue doing that. So this map, these red arrows I've drawn in, they will map to all of the positive integers. But the beauty is we've got a load of natural numbers left over, which we can use to map to the remaining numbers. So 2 can go to 0, 4 can go to -1, 5 can go to -2. Sorry, not 5. Oh, God. 6 can go to -2. 7 is used up. 8 is still available. 8 can go to -3, etc. So the rule for this map is if n is odd, we make phi of n. You're mapping 1 to 1, 3 to 2. So what we're doing is we're +1 and subtracting half. Yes, we've got n plus 1 over 2. Okay, that's the rule that sends 1 to 1, 3 to 2, 5 to 3, 7 to 4. You add 1 to the odd number n, and then you take half of it. And if n is even, so what are we doing to the even numbers? We're mapping phi of n. We're making phi of n. So 2 goes to 0, 4 goes to -1, 6 goes to -2. So we're sending it to n -2 divided by 2. We're sending it to the negative of that. Isn't that what we're doing? So does that work for 8? 8 minus 2 is 4, divided by 2 is 2, and send it to -2. Does 8 go all the way to -2? No, I send 8 to 3. No, 8 minus 2 is 6, divided by 2 is 3, we send it to -2. Yeah, so that's the right way. So figure it out. Okay. So this is our definition of our map. And you can kind of see, I messed up some of the arrows there. I tried to draw a second arrow of 5, but this map is bijective. We have counted in this proper way, attaching the counting numbers one by one in a bijective fashion. We've counted the integers using the natural numbers. So Cantor says that the size of the integers equals the size of the natural numbers. They have the same cardinality. And if you've never seen it, if you've never been confronted with that before, it seems kind of paradoxical, okay? Because you're still thinking back to, but surely look, n is within z, n is already sitting inside z, and then there's a whole other negative copy of it. So surely z is twice as big as it. Well, if you look at it that way, you kind of convince yourself it is twice as big. But then you look at it a slightly different way, and we see that there is a way to count all of the integers using the natural numbers. So, in other words, we say z is countable. It's countably infinite. It is infinite, but we can still count them using the natural numbers. Okay. What about the rational numbers then? Surely Q is much bigger than Z. or n. Okay, we've already convinced ourselves that the integers are the same size as the natural numbers. I could still be a little bit worried of it, but we've seen the bijection. Fine. But think about the rational. I mean, how many rationals are in here? How many rationals are inside the interval between 0 and 1? 5. How many? An infinite number. Yeah. How many inside the interval 2 to 3? An infinite. Okay. 2 to 3 also contains an infinite number of rational numbers. Because the rational numbers consist of all the fractions of integers. You can make the denominator as large as you want, and that potentially can give you rational numbers, on a very, any tiny, arbitrarily small scale. Okay? So there's an infinite number of rational numbers here, there's an infinite number here, there's an infinite number here. In any interval you look at on the number line, there's an infinite number of rational numbers. So surely there's way more than that there are the integers. And this is where what Cantor was saying really started to upset people. Okay? Cantor would say that the size of the rational numbers equals the size, let's say equals the size of z, which is equal to the size of n, we've already seen. Rubbish. How could they be the same size? There's an infinite number of them anywhere you look. Okay? But we need to count them in a clever way. So the way we're going to do it is let's count q plus, the set of all the positive rationals. If we can count q plus, we count all the positive rationals, then we can certainly count all of q, because we can just use this same technique here where if you count one set, then you can also count it using the odd natural numbers, and then you can use the even numbers to count another set of the same size. Okay. Well, you see, you can lay out all the fractions with denominator 1. So what positive rational numbers do you have with denominator 1? Well, you've got 1 over 1, 2 over 1, 3 over 1, 4 over 1, 5 over 1, etc., etc. Denominator 2. What rational numbers do you have with denominator 2? Well, you've got a half, 2 over 2, 3 over 2, 4 over 2, 5 over 2, etc., etc. You get the picture. Denominator 3. Now, if you haven't seen this before, this just looks like I'm just pointing out how there is more rational numbers. So what happened there? 4. This looks like I'm just emphasizing the fact of how many rational numbers there are, and that there's way more positive rational numbers than there are natural numbers. Because you look at this picture and you see, well, even in the top row, there's an infinite number of rational numbers, and you can count all those with the natural numbers, and then you haven't counted any of the other rows. Okay? But we don't count along one row first, because you'll never end, because each row is infinite. So you have to count in a different way, and you count by doing this kind of diagonal scanning. So what I'm doing here is I'm just drawing a path through the positive rationals. And we just think about the properties of this path. Okay, you're just scanning it diagonally. So you're sweeping across the infinite rectangle this way. So that's a path. At each step you're stepping on to the next number in the route. And if you've got a path, you can count the number of steps in the infinite path is countable. So take the first step, the second step, the third step, the fourth step, the fifth step, the sixth step, and so on. But you see here that this path will definitely reach every positive rational number. If you shout out any positive rational number to me now, in principle, I can tell you when the path will arrive at that rational number. Even if you make it so it's got a ginormous denominator, a ginormous numerator, so it could be way, 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 way out there, like down here. A rectangle starts up there, your rational number could be millions of miles away down there, but eventually this path will get there. Because it's making progress along each row. It takes an awful lot of time to reach a row that's far down the table, but it will eventually hit the first element. And if you wait long enough, it will return and scan back down and hit the second element in that row. And you wait a bit longer, it will return back and hit the next element in that row. Now there's a slight technical thing here. Sometimes we meet the same rational number again. So for instance, I met the rational number 1 up here. I also met it again here, 2 over 2. I also met it again here, 3 over 3, 4 over 4, etc. But if you want, we can step over these as we reach them. So what this picture shows, so we can step over those repeated rational numbers or just skip them. So this shows we can count all the positive rationals. And if you can count all the positive rationals, so by count we mean with the counting numbers, 1, 2, 3, 4, 5, 6, etc. You can count all the positive numbers, then you can easily extend it to all the rational numbers, positive and negative, by adjusting this counting scheme so that instead you count all the positive ones with the odd numbers and count all the negative ones with the even numbers. So you can then extend this counting to all of Q using our odd-even trick. So Cantor is saying that there are the same number, we should regard the rationals as having the same size as the integers. And this really rubbed people up a lot the wrong way because people kept coming back to this picture and saying, no, you don't understand, there's an infinite number of them here, there's an infinite number of them here, there's obviously far more rationals than there are integers. Then Cantor says, no, you don't understand. I can take a walk through all the rational numbers. It's a long, slow walk, it's an infinite walk, but if you name me any rational number, I can calculate and I can tell you I'll reach that rational number at step 10,000,007. Eventually, I will reach any named rational number. Therefore, I'm going to walk through all of the rational numbers in my infinite walk. Okay? So these were controversial ideas at the time. Some people embraced the ideas and realized that, oh, this is great, we're finally able to talk systematically about infinite sets, and we've got this new insight into how to speak about the size of infinite sets. Okay? But there was a lot of resistance to it as well. Okay? Particularly, you see, when resistance to it from people on the theology side as well. Okay? Because when you get into talking about infinite things, infinite and things outside the physical, often regarded as being in the domain of God and so on. So some people would have regarded what Cantor was doing was kind of stepping outside of boundaries and making assertions about the infinite, which in the society where Cantor was working, there was often a lot of overlap between the science, between the mathematical and the philosophical and the theological and the religious world. Okay? And that this kind of advanced abstract study would often kind of bump into the other disciplines. Okay? So there was there was something of a religious element to the controversy surrounding this as well. Okay, so we Cantor seem, you might get the impression here that you can count everything. Maybe we can count everything. And this is where the story really got interesting. Cantor showed why R should be regarded as not being the same size. Genuinely bigger than any of these lesser number systems, the rationals, the integers, and the natural numbers. And the way he showed this was using his diagonalization argument. Okay, this one is kind of a diagonalization, but the diagonalizational argument refers to his proof of why you can't count the real numbers. So this is the assertion: you cannot count R plus. Well, we cannot count the reals in the interval 0, 1. This is what he asserted, okay? So not only can we not count all the real numbers, we can't even count the ones that are located in the interval between 0 and 1. And it's a proof by contradiction. Suppose we could count the real numbers inside the interval 0 to 1. Suppose we did have a bijection from the natural numbers, the counting numbers, 1, 2, 3, 4, 5, 6, to all the real numbers inside 0, 1. So we think of the real numbers in 0, 1. Think of these in terms of their decimal expansions. Every real number inside the interval 0, 1 has some kind of decimal expansion, 0 point something. So suppose we could have counted these. So if we could count these, then we would have a bijection from the natural numbers, counting numbers, to all of the real numbers inside the interval 0 to 1. So let's just start to write down what this might look like. Okay, I'm just putting numbers down off the top of my head, random lists of numbers. If we could count them, we could assemble a table like this, okay, which has an infinite number of rows indexed by the natural numbers, and in each row, sorry, I should put in a dot, dot, dot. In each row, we have the real number from 0, 1 that we've counted with that natural number. Yeah. So if we could count all the reals in 0, 1, we'd be able to set up this kind of a table, conceptually. Counters the diagonalization argument. It's very clever. It asks a question about where is this number, and we construct this number from the table. So we look at the first position, this 0, so we look at that 2, so we're going to make this number be a 3. And you look at this number, so we're going to make the second digit of it a 1. And then we look at the third decimal digit of the third real number, and that's 3, so we're going to make this 4. We look at the fourth decimal digit of the fourth real number, that's a 4, so we're going to make this a 5. So you can see what I'm doing. I make the nth, ensure the nth digit of this differs from the nth real number, because we're supposing we could count them, ensure the nth digit differs from the nth real number ensure the nth digit of this differs from the nth digit of the nth real number. So the first digit of this differs from the first digit of the first digit. The second digit of this differs from the second digit of the second. The third digit differs from the third digit of the third. Okay. So this number cannot be on the list, can it? Because where can it go? Suppose we've counted all of the real numbers between 0 and 1. So if we have this real number, which is a real number between 0 and 1, it must be somewhere on the list. But wherever it's supposed to be, it cannot be there. Like, supposing it was at position 6. Well, it can't be in position 6 because its sixth digit is going to be different to the sixth digit of the number in position 6, because that's the way it was constructed. So we construct this real number in such a way that ensures that it cannot be in any position on the list. This is a contradiction. And you worry a lot when you reach a contradiction because maybe you stumbled upon the fact that everything is a contradiction, that things are true and false. And you better send a letter to the Times or something about it. But put it on Twitter that everything is true and false. But it's not. Okay, so we have arrived at a contradiction, not of something that is definitely true. What we found is a contradiction of this assumption that we made. We assumed that we could count. And that leads to a contradiction. So the conclusion of the argument is that it is impossible to count the real numbers. Because if you could do it, everything would be true and false. And there'd be chaos everywhere. So R is genuinely bigger. As there cannot be a bijection. Counting method from the natural numbers to the real numbers. So what Cantor showed with these ideas is that it isn't just there's finite sets and then there's infinite sets. He showed that within the universe of infinite sets there are different kinds of infinity. Okay? You have small, manageable infinities that you can still count, like the integers and the rationals. But then there are these kind of hyper-infinities. The amount of real numbers in the real number system, you just can't count it using the natural numbers. And so there's a whole huge field of pure mathematics, which is set theory, which investigates and classifies and describes the whole hierarchy of infinite sets. Okay? So there's at least two infinities, countably infinite, and the infinity that is the measure of the real numbers, which is bigger. But we've seen that there's at least two, but there's many more. Okay. And that's not a joke, because there's an infinite number. It's just a wonderful, ever-growing, ever more complicated hierarchy of infinities that you can imagine and construct in set theory. So if you're interested in reading more about this, I've given a number of resources down here in the notes. Some good material you can look up. It's fairly readable in the Stanford Encyclopedia of Philosophy. So this kind of stuff really gets you into the intersection between mathematics and philosophy, because you're down at the foundations of mathematics here. What really are mathematical objects? What really are numbers? How can you construct them in a rigorous way? And that gets you into set theory, but then you're forced into considering different sizes of infinity, and then philosophers worry about it because philosophers are interested in such things. So there's good material in the Stanford Encyclopedia of Philosophy you can read. It's fairly readable. And there's a good BBC Horizon documentary called To Infinity and Beyond. It has a lot of mathematicians in it. I believe that's still available on the iPlayer, as they say. Yeah, Sarah? So that's an episode of the BBC Horizon. This is Timothy Gowers, well-known British mathematician. And others there. And there was, where's it going? There was another document. Now this is an illegal, yeah, he's gone. So there was this other, it was a drama. It was like a short play made on the theme of this, about a story called Dilbert's Hotel. Dilbert's Hotel, well, David Hilbert was a mathematician, famous German mathematician around at the time of Cantor. He was one of the ones who did embrace Cantor's new view on mathematics, and he was really trying to push mathematics forward at that time. And there's an interesting story about a hotel called Hotel Dilbert, which has an infinite number of rooms, and even when it's full, it can still take in more guests. Okay? So it's an infinite hotel. It's got room 1, room 2, room 3, room 4, and even though all of its rooms are occupied, they can still fit in an extra guest. So how do they fit in the extra guest? Anyone who's seen this story?
They move the room by one.
Yeah, so someone new arrives and all the rooms are occupied, but they just ask everybody nicely to move up to the next room, and that vacates room 1. So the new person can go in room 1, everyone else is happy because they only have to move up to the next room. And so they've squeezed one more person into the infinite hotel. And you can take that story and run from it. What if an infinite number of new people arrive? You can still accommodate them. Unfortunately, that drama, it appears from time to time on YouTube, but then it gets taken down. It's still under copyright and so on. But you should check out the others. Okay? Okay, thanks for listening. Next week I'll do some revision material.